What's today's date? 19th. Okay, well on November 19th, let us take a look at this. Okay. You don't have to write it all down. Although, it would probably be a good idea for you to write it down because then you'd remember it. As a teacher, I know that when I get students to write things down, they remember it a lot longer than if they just hear it. So, anyways, but this table is up now on the website. So, what I have done is I have taken, just to try to give a comparative representation of the energies of these various events. So I've taken the data and I've presented it in two ways, into table and the graph. And I've started with the basic unit. The smallest one was the fission bomb, the little boy bomb, that was dropped on Hiroshima back in August 6, 1945, that had an energy release of 15 kilotons. How much is a kiloton, Sam? Equivalent to? That's right, Dennis. It's 1,000 tons of TNT. So 15 kilotons means 15,000 tons of TNT. And that would be enough to blow up several square blocks around here. 1,000 tons of TNT.
A kiloton would be 2 million pounds.
Yeah, 1,000 tons, it would be 2 million pounds of TNT. 1,000 tons, 2 million pounds of TNT, right. So that times 15 gives you the scale of the Hiroshima little boy fission bomb. And then the Nagasaki bomb was actually a little bigger. It was a plutonium bomb rather than a fission bomb, and it was more similar to the first one that was detonated over by Alamogordo, New Mexico in July, which was Trinity, and that was about 20 kilotons. At the time that the bombs were dropped at the end of World War II, there was exactly 2 in our arsenal. There was one that was done as the test, and then they finished the 2 more, and they were August 6th and August 9th. Okay, now by the 1950s, they had learned how to increase the power of the bombs. You can see in a large atomic bomb would get up to like 200 kilotons. That was typical for a large atomic bomb. And then, of course, then they went to the hydrogen bomb, because the hydrogen bomb is a fusion bomb, and it takes more energy to trigger the fusion than it does the fission. But once they had the atomic bomb, they were able to use the atomic bomb as the trigger for the hydrogen bomb. And now we're talking about megatons. And a megaton is 1 million tons of TNT.
2 billion. 2 billion.
2 billion pounds of TNT. So that's enough. 1 megaton wouldn't wipe out the whole urban area of Atlanta, but it would probably easily wipe out half of it. Half of it. At least you could figure that the radius on that would probably be about 5 miles of total destruction in every direction. 1 megaton. Now, what is the largest hydrogen bomb warhead ever tested and or deployed by the United States? 20 megatons. 20 megatons. What was the largest hydrogen bomb ever tested by the Soviet Union? 60, right, 60 megatons. What was the size of the Tunguska event? Well, let's see, it's not on this one, but now see, I've started, the chart starts with nuclear bombs, because in the human scale of things, those are the biggest energies we humans have ever been responsible for releasing. And now if we look at Mount St. Helens eruption, in the first 3.3 seconds of the explosive eruption on May 18th, it was 5.7 megatons. So that's the size of a hydrogen bomb. It's the explosion, that explosion of Mount St. Helens, then you can see was in the same scale range as a hydrogen bomb going off. The meteor crater asteroid impact, 6 to 10 megatons, so that's about the same size explosion as the Mount St. Helens. And then you have the San Francisco earthquake of 1906, which was 8.3 on the Richter scale. It was equivalent to a 12 megaton explosion. So if you were to take a 12 megaton hydrogen bomb and do an underground detonation under San Francisco, that would be equivalent to what happened in 1906.
What about the 89 earthquake?
The 89 earthquake wasn't that big. I don't know the size of it.
Sure felt like it.
It was quite a bit. I mean, wasn't it 6 point something?
Yeah, but that was.
Well, first of all, they're completely different. A volcanic eruption and an earthquake is a totally different type of energy release. But, you know, because most of the release in that earthquake went through the crust of the Earth. Most of the release of the Mount St. Helens went into the atmosphere when it exploded.
Yeah, you can see that.
Yeah, and I mean, and that was obvious from the radial tree fall. There was a pressure wave that went out with a huge amount of energy. Just like with Tunguska, there was a pressure wave that went out that had a huge amount of energy. I don't think we need to split hairs over that. I mean, this is a relative. This is based upon scientific estimates. That's what I've used. I've gone to respected sources that have studied these, and that's what they, have come up with. The volcanologists that looked at Mount St. Helens, I mean, that's where I didn't make that up. That's geologists and geophysicists and volcanologists that came up with the 5.7, even to the degree of precision that they've got it to the 3.3 seconds. And, there have been seismologists that have studied the San Francisco earthquake in great detail. There are seismologists that have devoted years of study to that, and that's what's led to that 12 megaton. So, what I would probably suggest then, Jerry, is that you maybe contact some of them and tell them, point out to them where they've gone wrong.
One question. Would a well-placed hydrogen bomb trigger an earthquake or a volcanic eruption?
It could, yes. Yes, absolutely it could. And there's been some, when we were still doing a lot of subterranean testing up through the 80s, there was some interesting correlation studies done showing a correlation between underground testing and earthquakes. That's not inconceivable at all. Yes, Linda?
When they were setting off the bombs in Nevada back in the 80s, those underground things, every time they would set one off, within 3 days we had a fairly good-sized earthquake in San Francisco. Within 3 days. I could always tell when we were going to have a big, a fairly good.
Yeah, and that's not at all. There's nothing inconceivable or far-fetched about that.
Also changed the weather on the other side of the world from where the bomb was.
Now that I don't know about. That's a little bit more of a stretch.
Am I missing something here? We're just looking at this graph to get an idea of...
No, I'm trying to move through it here, but we keep getting bogged down. Otherwise, we could have probably been on the third or fourth chart by right now. Okay, now we get to the Tunguska, and we got 15 megatons. And notice that we have a nuclear test that's about the same size. Tunguska is merely an estimate. The estimates range from, that I've seen, are on the low end 5 megatons and the high end 50 megatons. Most of them have fallen within that range, somewhere around a 15 megaton explosion. You asked about the Alaska quake, and that's a 24 megaton. So that was pretty darn big, and that's 8.6. So you can kind of get a sense of how an earthquake might compare to a nuclear blast or a small extraterrestrial event like Tunguska. And we see all-time largest hydrogen bomb, 57 megatons. And then we get to the Steinhem Basin, Germany. See, it's a crater 2 miles in diameter, and you can see it's 125 megatons. So it's now beyond anything ever in the largest nuclear arsenal. Notice that notice how close it is to the largest ever recorded earthquakes, which is 8.9 on the Richter scale. So that'll give you a sense of comparison. You've got an impact of an extraterrestrial object creates a crater 2 miles in diameter, and that's roughly equivalent to the largest ever recorded earthquake, which at this point is generally estimated to be 8.9 on the Richter scale. And there were 2 of those now, one in Japan in 1933 and one in Colombia in 1906. So that one in Colombia in 1906, what was the date? That's February 14th. And the date of the San Francisco was April. I wonder if those were related. The 2 huge earthquakes like that sort of happened back to back. But that gives you a sense. I'm trying to put this into a perspective for you. So now we're leaving, if we go beyond 8.9, 9.0 on the Richter scale, we're in a whole nother realm altogether of earthquakes which probably are not going to happen. And the reason is that rocks have a limiting strength. In order for a bigger earthquake to happen, the pressure has to be able to build up, right? It has to build up before it can have this sudden release. The problem is that the rocks are generally not strong enough to allow, they fail before the stress can build up to that level. So if you're going to have an earthquake beyond what we're seeing right there, let's call it 9.0 on the Richter scale, we probably have to introduce something else altogether, like, boom, this, the fist from space. See, now you'll see that what we've gotten there is a crater 2 miles in diameter, would be bigger than any hydrogen bomb explosion. A hydrogen bomb explosion couldn't quite create a diameter 2 miles in diameter. Yes, Don?
Do you know what size rock would cause a crater 2 miles?
Here's what you use. For the crater, take the crater diameter, and the object is going to be between, the crater is, let me turn it around. The crater will be between 10 and 20 times the size of the object. That depends on the density of the object, the velocity of the object, the angle of entry, and also the constituent of the target rock. All of those things will affect the ultimate crater size. But as a general rough rule of thumb, 10 to 20 times the size of the object is the crater. So you take 2 miles, let's say a 2 mile crater.
1 to 2 blocks wide.
Yeah, so let's say a 2 mile crater in round numbers is 10,000 feet. That means that the object is going to be between 500 feet and 1,000 feet in diameter. But then again, that's going to be what the thing, the velocity of the object. If you can, by this time, hopefully you've got enough understanding of these processes, just in our discussion about the torrid meteor shower, that you know that if we're moving through space at 18.5 miles per second, and we come upon like the June meteors, the Tunguska meteor, it came in from the direction behind the Earth, you see? Now on November 1st, when we're crossing the stream coming into the sun, we're going at right angles to it. You see, so now if we're moving this way and it comes from behind us, you have to subtract the Earth velocity from the absolute velocity of the incoming object. And that's probably one reason why the Tunguska object was seen by so many people, because it was moving slower than an object that, for example, if we met the Tunguska object head on, we would have had, the two velocities would have added, you see. If the Tunguska is moving 20 miles a second and the Earth is moving, that same amount, you add those two. Well, the amount of energy released is going to be the square of the velocity. So if you doubled velocity, you've increased the energy by 4 times. So if we'd met Tunguska head on, it would have been much more devastating than having it come from behind. So see, that's a factor too. The crater size is going to be a function of how much energy is injected into the Earth's crust. That's going to be a function of the direction at which the object comes in. The most devastating would be a head-on collision, just like in your car. And less devastating would be a rear-end collision. And that's what Tunguska was. Tunguska was a rear-end collision.
That small one that came into South America last year, they said, well, we didn't think anything this small would hit. It would always burn up. I think that would be a factor, how something only 3 to 6 feet in diameter could actually come in and make a crater.
Oh.
Because it was, it was coming up behind us or something, and the velocity was much less. But they didn't bring that up.
An iron meteorite, a small iron meteorite, can be, an iron meteorite can be a lot smaller than a chondrite meteorite.
Yes, that's a very important point. And also in understanding the nature of the terrestrial environment we're going to have to deal with, is that it's if we take all of the craters there are, most of the craters are going to most likely have been created by high-density objects. Because the high-density objects are the ones that slam into the Earth and make the craters. Lower density, like Tunguska, don't leave craters. Well, the important thing is when trying to take a determination of the near-Earth population of things, you have to look at both of them. You can't just do crater counting, because that's going to be off by a factor of 10. Because for every object, say below a couple of thousand feet in diameter, that can actually strike the Earth's surface, there's between 5 and 10 objects that would blow up in the atmosphere before they hit the surface of the Earth. So what that actually implies is that Tunguska-type explosion events in the atmosphere are going to be more common than cratering events that actually leave permanent scars in the landscape that geologists can then go around and count and use as a statistical database to determine how often Earth is struck by things from space. Because Earth is struck from things by space much more frequently than one would be led to believe only by crater counting. And yet a lot of the studies that you see, particularly the ones that have been in mainstream media and in a lot of the documentaries that I've watched and so forth, are based strictly on crater counting. And it's likely, again, for every one that leaves a crater under, say, 2 miles in diameter, there were more objects that didn't leave a crater that would have released their energy into the atmosphere. Now, if you had a multiple Tunguska strike, you could have, tens or even hundreds of objects coming in that don't leave a crater, but can inject enormous amounts of energy into the atmosphere, certainly enough to affect the global climate. And who knows what else. Let's proceed on here. So the impactor that made the Steinhem Basin 2 miles was probably somewhere then between 500 feet and 1,000 feet in diameter. And depending on, whether it was a stony object or an iron object, whether it was a head-on collision or a T-bone or a tail end, rear end, is going to affect it. So we don't really know. But it gives you the range of the thing, and a 2 mile diameter. Now the other threshold that's important here is that a 2 mile diameter is now you're talking about an event that's large enough to begin to have a global effect. The second page of my graph here basically ends with the energies released that would begin to have a global effect. Now, a Steinhem Basin impact leaving a 2 mile crater, let's say that happened in Germany today or tomorrow. Well, you could pretty much kiss most of Europe by. Certainly all of Germany would be gone. And a lot of Europe, would have lost, millions of people. Over here, what would we experience here in the United States? Well, what we would probably experience here is a global climate cooling that might last 2 or 3 years because of the amount of dust injected. And it could end up being very socially disruptive for us, particularly if it caused agricultural collapse, which when we're talking a crater 2 miles in diameter, we're at the stage now where less than that, we're probably going to be able to weather it fairly okay. That's kind of like the threshold. 2 miles and up, we're definitely going to have to deal with consequences, absolutely. So that's sort of the cutoff point of the second page of the graph. Now as we get into the third page, we're definitely talking about events that could have a global scale. Krakatoa, 200 megatons, ejected 5 cubic miles of material, and it caused a global, one of the coldest winters of the 19th century. If we go down to eruption of Crater Lake, Oregon, 6,600 years ago at the dawning of the age of Taurus, which I find an interesting correlation, 550 megatons, and that eruption, who's been to Crater Lake? Or at least know what I'm talking about. The big round lake, I haven't been there yet, but that's a volcanic eruption. 550 megatons, it ejected 12 cubic miles of material. So you can see it was over twice as big as the Krakatoa eruption. I don't know if you've ever read the accounts of Krakatoa, but they're pretty extraordinary. And the tsunamis generated by them. Crooked Creek, Missouri impact. See, now we're looking at 4.3 miles in diameter, and notice the megatonnage, 1,792 megatons. So a 4.3 mile diameter crater is definitely going to have global consequences. If that event happened today in Missouri, you could figure the whole southeastern United States would probably be wiped out by the secondary fires, the blast wave, and so forth. People 1,000 miles from the blast are going to survive, but life is going to be pretty tumultuous for a couple of years after that, for sure. Upheaval Dome in Utah, 6,000 megatons. Here we're now 6 miles in diameter. And notice the date of the Upheaval Dome in Utah. Its date puts it right at the Cretaceous-Tertiary boundary, suggesting it could possibly be a part of the big boy that struck the Yucatan, or part of a swarm. That might have been part of a swarm, because there's actually a handful of craters now that are all clustered around that KT boundary. Then we get to the very bottom, and we see that the total U.S. and Soviet nuclear arsenals in the early 1960s, during the period of mutual assured destruction, was 10,000 megatons in round numbers. So if you've ever contemplated the effects of nuclear war, I mean, it's been pretty agreed by all folks that all-out nuclear war would be globally devastating. Probably not cause the extinction of the human race, but there again you have to factor in the consequences of radiation.
How do the Carolina Bays compare with all this?
That's a good one.
Did you hear they're talking about this forestry thing that the C12 that's usually in the atmosphere became C14 because of the testing we did?
Yeah, I'm not really knowledgeable about it, but yeah, I know that there was radioactive carbon as a byproduct of the
trees by looking at the effect
yes.
of C14.
Yes.
Trees all over the world, not just
right.
In the Pacific where they were
right.
doing the testing.
Yes, the atomic bombs have left their signatures in tree rings. Okay, so get that in your mind, 10,000 megatons. We all know whether we assume it's going to cause the extinction of the human race. I don't think it would, although a blast from something from space is not going to have the associated radioactivity as the nuclear detonations. So while the energy releases would be equivalent, the secondary deaths from radiation would not be a factor in an impact event. Let's keep going. The Tambora Eruption of 1815. Now this was the one where they called it the following. Notice that it's in the spring of 1815, and the following summer they referred to as the year without a summer, in which there was snow falling all over Europe in July and August. And that was directly the result of the Tambora volcanic eruption. And you can see there, it put 36 cubic miles of matter into the atmosphere. And you'll see that the approximate energy released was estimated to be 20,000 megatons. So it was the explosion that would have been the equivalent of taking double our total nuclear arsenal and detonating them in one place. And now notice the Santorini, the 1470 BC, somewhat bigger, but in the same scale as the Tambora volcanic eruption. But you know the 1470 BC, that's the one that wiped out the Minoan civilization and the civilization on Crete, and left, which has caused a lot of antiquarians looking at to assume that the Santorini volcanic eruption was the source of Plato's tale of Atlantis. In fact, that's the leading theory about Atlantis, is this one right here, the Santorini volcanic eruption. Next one should be a familiar one we've talked about in here, Yellowstone eruption, 27,000 megatons, 2 million years ago. It ejected a total of 600 cubic miles of pyroclastic material. So an explosion like that would be very, very serious. Very few people in North America would survive that.
Covered 97% of the United States.
Yeah. Okay, then we get to another impact, which you can see is 14.4 miles in diameter, and it happened 15 million years ago. 118,000 megatons. So basically 10, 11, almost 12 times the total energy of the world's nuclear arsenal in the early 60s. And the date of approximately 15 million years before present is an interesting one, because that puts it pretty close to the beginning of the outpouring of the Columbia Basalt Plateau. All of those, there was major eruptions, fissure eruptions around 15 million years ago that caused that, and several geologists have speculated that that might have been due to an impact that buried itself deep into the mantle. And you know, there's a connection between the Columbia Basalt Plateau and Yellowstone because you have a mantle plume. Everybody understands what a mantle plume is, right? That you've got a upwelling, an extreme upwelling of heat coming up, and you have the Earth's crust, due to continental drift, is riding over this mantle plume, right? So around 15 million years ago, there was a whole series of fissure eruptions in the area that is now bounded by southeastern Washington, northwestern Oregon, and Idaho. There's an area right in there that's full of these weird cracks that all of this magma poured out and concentrated around 15 million years ago. Now, in the 15 million years since that has happened, the plate has moved to the point where now over that mantle plume, Yellowstone is over that mantle plume, the same one. It could be that the original Yellowstone eruption was related to an impact, if that's true. And likely, what we're talking about here would be an impact of an iron object, very dense, and probably a head-on type collision, where something could go straight in and bury itself deeply into the molten part of the mantle, rather than coming in at an angle or being a low density, so it distributes most of its energy in the outer layers. If it's a heavy iron type asteroid, strikes the Earth head-on collision, comes in almost at right angles to the surface of the Earth, it can bury itself, and that's one of the theories that may have been what originated this huge outpouring of basalts up in the northwestern United States around 15 million years ago. So notice what I'm calling your attention to is that around that same time there is a confirmed impact in Europe. And then we get the total for all late Wisconsin Missoula floods. And that's based upon 40 megaflood events. And notice where its energy range is, 180,000 megatons.
So how do you regard the 40 megaflood events?
Well, I think that's probably in the proper amount. See, one Missoula flood, one draining of Lake Missoula, for easy figure 500 cubic miles of water. Okay, 500 cubic miles of water being one draining. Now, if you start out and you have 500 cubic miles of water and its surface, its bottom is at 2,000 feet above sea level, its surface is 4,000 feet above sea level, then you release that potential energy and it flows down to the sea level and becomes converted to kinetic energy. That's how you would calculate this energy right here.
Do you believe there were 40 of them?
No, I don't. However, if you take 40 times 500, what's 40 times 500? 4 times 2,000, 20,000. I do believe that 20,000 cubic miles of water is closer to the, conservatively, closer to the real amount of water we're talking about in any given flood. Rather than 500 cubic miles, 20,000 or more cubic miles poured over Washington. So in that respect, I do think that 40 is going to be closer. In fact, you know, the estimate now is the biggest one is, they're saying that there's maybe 80 to 90 floods, each one which would be a separate Lake Missoula. Now we're talking about 40,000 cubic miles of water involved. So the whole question of the Missoula flood is still, you know, I mean, I've spent a lot of time on that because I think it's probably one of the most important unresolved scientific questions of our day regarding the history of our Earth, particularly the recent history of our Earth. Because you can see from this, and this what I want to emphasize here, is that somewhere or another there has to be a source of energy that causes, you can't just release, you know, 20,000 cubic miles of ice without there being an energy source. You know, if you're going to do it by uniform means, you would assume that the climate warms up and you have more solar heat, and this produces melting, and the glaciers would then recede, just like we saw with the termination of the Little Ice Age. Worldwide, glaciers have receded in the last 200 years, right? We know that. In the last 150 to 200 years, glaciers worldwide have diminished in size to half or a quarter of their previous size during the peak of the Little Ice Age. But when we look at the level of catastrophic flooding, there is nothing even remotely related to the flood discharges here, you see. And my point is that you've got to have, in the case of the Little Ice Age, I'm going to assume what caused the recession of glaciers was probably an increase in the amount of solar heat. What else would it be? Because the glaciers begin melting before humans had any discernible impact, 100 years before humans were having a discernible impact on the global temperature. So it had to have been some natural mechanism causing the climate to first to warm into the medieval warm period, then to cool into the Little Ice Age, causing global expansion of glaciers, then another warming causing a global contraction of glaciers. So you don't have the global contraction of glaciers without the energy source from somewhere. And I'm going to guess that it's probably the sun. However, you try to apply that to releasing 20,000 cubic miles of ice and converting it into water, no kind of solar effect is going to accomplish that unless you somehow many times over magnified the heat of the sun, which, you know, no astrophysicist I don't think could come up with a way you would do that and not just cook the whole Earth. What you have here is a concentrated injection of energy that's sufficient to convert thousands of cubic miles of ice into water. And there, I think we're getting on to trying to identify what exactly it was that happened that created this turning point in Earth history and human history 12,000 years ago. So, see, that's what the circumstantial evidence suggested to me almost 2 decades ago that that's what it was. Because I got led to the study of the Missoula floods through the study of the Carolina Bays. Because I theorized that with the Carolina Bays, if it was a multiple fragmentation event coming from the northwest, and it occurred 12 to 13,000 years ago, or towards the end of the Pleistocene, it then occurred during the Ice Age. Well, if you follow the incoming path, 45 degrees northwest, if it was a multiple fragmentation event of a extraterrestrial object, then it means it had to have passed over the ice sheet if it did it during the late part of the Ice Age. The ice sheet was there, it came from the northwest, it would have passed over Canada. So indirectly then I began to look for evidence that such a thing may have happened. So the question that I framed in my mind was, if there was a multiple fragmentation event that led to the formation of the Carolina Bays, is there any evidence of unusual effects during the deglaciation period? So then I began to look into that, and then, whoa, there it was. I mean, from all across the southern margin of the ice sheet, the evidence was coming in that there had been these gigantic catastrophic floods coming off the ice sheet. You know, I mean, literally, that could only be measured in millions and hundreds of millions of cubic feet per second, with the most spectacular ones, of course, being the Missoula flood in the northwest, but documented all the way along. There was gigantic floods that came down the Mississippi River, gigantic, huge floods. There were massive floods that came down and swept over the Dakotas and Montana. I mean, those complete states were probably almost underwater temporarily, like an inland sea just moving across North America. And I'm going to show you something before we leave tonight, some recent satellite photographs that really bear this out, and the scale that these sheet floods would have been taking. But the point is, something had to have introduced the energy initially into the system. Now, can we theorize from that, and can we say, well, it was a bolide, it was an asteroid or a comet, and we've solved it and there's no more question about it, let's move on to the next question? Well, of course it's not that simple. Nothing in science ever is. All we can say for sure at this point is something very, very extraordinary happened. And by default, it was almost certainly something extraterrestrial. But beyond that, what was it? We get into the realm of speculation. Now, a couple of years ago, the finding of the black mat. Have I shown you pictures of the black mat? Okay, good. I've got some to show you tonight. The black mat. The discovery of the black mat is so profoundly significant in promoting a major paradigm shift about our Earth that it should be something that they're talking about, you know, it should be a major topic of discussion, but it isn't. I mean, basically, it's the evidence that our whole planet was engulfed in some kind of an extraterrestrial event 12,000 years ago. And what was it? I mean, it couldn't, see, and it's too complicated to be explained by a single impact. So then that leaves multiple impacts. But was it multiple impacts? Again, we don't know for sure, but we know that the largest loss of species in 5 million years occurred right at that same time. So, and then we're also confronted with the fact that the dominant theory for the disappearance of those species was, for the last half century, has been us. In all of the credible, so-called credible scientific explanations, we humans decapitated the food chain 12,000 years ago. And so that has allowed getting around the fact that, no, it's something else. Something else caused the decapitation of the food chain at the same time the ice underwent this catastrophic meltdown. At the same time, the climate went through a total spasm from full glacial cold to interglacial warmth, back to glacial cold, and back to glacial warmth, just like that. And that climate change, how does that correlate with the melting? Well, that's waiting for the new generation of Earth scientists and space scientists to look at. Because we don't have the answer to it yet. That's my point. We've confronted the reality that something extraordinary has happened to the planet, and it's probably happened multiple times. And that in between these intervals of these events, whatever they are, we've managed to create temporary manifestations of civilization. But what I'm getting, and what I want to get at here, and want you to grasp, is that Tambora volcanic eruption, if that happened now, how many people would die worldwide if Tambora happened now? Probably several hundred million anyway. Because if we had a northern hemisphere year without a growing season, the advanced industrial countries will survive with difficulty. All the rest of the countries are going to experience enormous starvation. And the problem is that with starvation, even if people don't die, they become weak, and their immune systems become weak. And this is when secondary effects can kick in, such as plagues and various types of epidemics. So when we get to the end of it, we're up at 200,000 megatons, and you can see you're talking a 20-mile in diameter crater, and we're still really at the low end of the cosmic scale. And I'm going to just jump on to the end of this. Now this, you can see I put it in graph form. So you can see scaled 1,000 tons, 1,000 tons or 1 kiloton is the far left, and a large atomic bomb of 200 kilotons is on the right. Yeah.
How do the impacts did have any effect on the speed of the planet or the orbit of the planet or changing?
Up to the scale that we've been talking about now, not really. Although they could certainly introduce perturbations that could be detected. But when we get up to the 10-mile or 20-mile diameter objects, yes, they could. Let's go through this. So now I've gone, the way this is set up, the largest bar on the right becomes the bar on the left in the next graph. So you can see large atomic bomb on the left is still quite a bit smaller than the San Francisco quake of 1906. And then we go taking the San Francisco quake of 1906 and moving it to the left of the graph, we see that it's still smaller than the largest hydrogen bomb, which is up there approaching 60 megatons in explosive energy. And then we go here now, largest hydrogen bomb is on the left, Crater Lake, Oregon is on the right. And here we have Crater Lake, Oregon on the left and total nuclear arsenal on the right. Now that we're at total nuclear arsenal, we're in the low end of the cosmic events. The energy's released in the cosmic events. In fact, you'll notice Upheaval Dome, Utah is close at 6,000 megatons. Have anybody ever heard of Upheaval Dome, Utah? I'll show you a picture of it later. It's a very interesting place. Total nuclear arsenal on the left, 40 Missoula floods on the right. So you can see the amount of energy. Now here's one way to think of it. If you took, notice that 40 Missoula floods on the right is 180,000 megatons, right? So here we have total nuclear arsenal at 10,000 megatons. So 10,000 goes into 180,000, how many times? 18 times. So think about this. In order to produce the amount of water to create those estimated 40 Missoula floods, you would have to bomb the ice sheet with our total nuclear arsenal 18 times over. There's another way to think of it. Think about dropping one hydrogen bomb on an ice sheet like over Greenland. Well, now think about the whole nuclear arsenal 18 times over. And the approximate amount of energy then injected into the ice, converting the ice to meltwater, that meltwater running off, that's the equivalent now of the amount of water produced that flowed across the Pacific Northwest during just those floods. And now we've got on the left 40 Missoula floods on the left of the graph and the Manicouagan impact structure on the right. The Manicouagan impact structure dates at about 208 million years ago, which was the Triassic-Jurassic mass extinction. So when you're talking about an event on the scale of Manicouagan, you know which one Manicouagan is, right? We've seen pictures. That's that ring lake up in Quebec. Largest impact structure exposed at the surface in North America is the in America is the Beaverhead, right here. Beaverhead, Montana, which is in the southwestern corner of Montana. And you'll notice I haven't even gone up to the level of like the Cretaceous Tertiary impactor. For those of you that really want to get this, I would say go to the website because I've got this whole graph. Everything we just looked at is now up on the website, along with a bunch of other stuff.
What's the heading or the title of all this to get to it?
This is actually if you go to the preliminary matters. Cosmographicresearch.org. A lot of the stuff on there will be familiar to you guys, but you know, there's the details, and you know, if you want to go say what was that specific fact, you might be able to find it on there.